Log on, tune in, find out. Another good idea from Cambridge.
I think this workshop is nice to visit here, and so I did the most important thing yesterday, and so I did some sightseeing, and so this is not a bad picture from an iPhone. So it's great to visit Cambridge and the Newton Institute. This is where I'm from. The Columbia University, if some of you may know, that is formerly the King's College of New York City. So I'm sort of visiting the other King's College here. King? That I don't know. Yeah. I need to look at my history book. But anyway, so this is something that I'm going to talk about. So what I'm going to talk about is comparatively simple compared to the previous talk. So I'm going to focus on the sort of the most standard problem in phase 1 clinical trials, in which the primary objective is to assess the safety of a drug, of a new treatment. A more specific objective is to identify what we call the MTD, the maximum tolerated dose. Let me see how it works. Yeah. And so the way we define maximum tolerated dose is that we want to identify the dose level with toxicity probability closest to a pre-specified target P. So pi of x is the DLT probability at dose x, and P is pre-specified. So this is a very simple problem, estimation problem to begin with, and all we assume about pi is actually just is increasing so that it has a solution.
But just a question.
Sure.
Let's look at this formula.
Right.
And let's assume that P equal, say, 0.98 or 99. So is it the same to get points where probability equal 1 or probability equal to 0.95, for instance? You see, you take
right.
a model here. It should be some kind of log or at least some kind of other distance between P and your pi.
Right.
This is not good metric. That's what I'm trying to say.
Well, first of all, in practice, so I think that two parts of the two answers to this question. First, in practice, P is usually on the low side, so it's with a relatively narrow range. I think in practice it's ranging about 0.1 to 0.3. So that's the range, and hopefully this metric holds up within that range. But I'm working, and the second part of the answer to this question is I'm using this as a definition so that we can focus on discussion in a concrete context. But we could actually extend the theory and result here to a more general matrix. But thanks for chipping in. And what I'm trying to do is to make things more and more specific. So what I'm going to do is focus on a particular method to this estimation problem, which is the continual reassessment method, the CRM. In a nutshell, what the CRM does is to try to treat the next patient at a dose that we believe is the MTD based on the most current data. So this is basically the scheme that we're doing. So if you compare this with the only difference is we replace pi dk with an estimate of dk. So intuitively it is quite appealing from an ethical viewpoint, in the sense that we're trying to be greedy. We're trying to treat the next patient at the dose that we believe is the best, and there are also advantages like so usually this is F is a model. I'm going to basically the whole talk is about how to choose this whole thing, and one thing good about using a model is that we can borrow strength across doses, and it is quite kind of flexible. This is one of the most interesting examples that actually happened early on in my career. And so for those of you who know about the 3+3 rule, which says that we escalate if we have 0 out of 3 toxic outcome of 3 patients, or 1 toxic outcome of 6 patients, and we de-escalate with 2 toxic outcomes out of 6 patients. And I think it happens early on when a clinician brings this data to me. So what happened is that they over-enroll. So they're supposed to enroll 6 patients. For some reason, they got the 7th patient, and then they get 2 toxic outcome, and then I didn't know what to tell them. So I didn't know what to do. So if you're using this paradigm, all you need to do is to estimate the toxic probability at that dose, and then assign the dose with toxic probability estimate to be close to the target. So this simple is flexible. So this is all good, with the big assumption that we're choosing the right model. So as you've seen throughout the day or the afternoon that we are dealing with a lot of modeling, and we need to calibrate the model, or we need to elicit the prior. So this is usually very complicated, and I'm going to illustrate how to do it in a simple setting. So, and hopefully the principle I developed here can be extended to the more complicated setting.
What's the B in your estimate?
I'm going to talk about B is, actually I can tell right now, B is basically the posterior mean, in this context, the posterior mean of the model parameter beta. But it could be the MLD, it could be some other thing, but if we use MLD, which is non-Bayesian, which is out of scope of this topic, and also it comes to the problem that it may not exist before we have data. So we're going to be very focused here, just for the sake of discussion.
And when you say calibrate, you calibrate the F or?
The whole thing. I'm going to show you, and this is one more slide to show you what can happen if the SARM is poorly calibrated. So this is a simulation result in which the target probability P is 0.2, and under this scenario, the dose toxicity curve at dose level 5, or actually this should be 6. At dose level 6 is 0.22, so this is MTD is dose level 6, and you see that the SRM with 25 subjects is correct only 28% of the time, which is bad. And what is worse than bad is if you double the sample size from 25 to, well, almost double to 48, you don't improve. That's a bad indicator that you don't only do it poorly, but you don't improve when you increase the sample size. That's a bad thing that we should avoid as a statistician, I think. And so this slide hopefully give you the motivation why we need to calibrate the model carefully. And it is not that easy.
Suppose you treat 480, so probably will.
No.
You won't.
Yeah, so what happened is actually there's a theoretical result saying that why it won't happen because it violates one of the conditions under for consistency for the CRM under this particular truth. So there's theory guided to, so basically this scenario is cooked up to illustrate that CRM fails. But we know how to cook up the scenario, so that's the thing. The question is the goal is to avoid this. And how we're going to do that, and that's the goal. And now, this is the outline of the talk, and basically I want you to spend most of the time on the first bullet here. Basically, I'm going to break down the CRM model, the F, the whole package, into 3 parts. The dose toxicity function, F, and then we have, for the model, we have it is indexed by parameter, which is beta. We are going to, so in a Bayesian context, we need to specify a prior for beta. So that's the second part, and there's another component that I'm going to talk about later is what I call the initial guess of DLT rate. But this will be the part that I focus on in particular. It depends on how hungry you are. I'll aim at these two, the blue contents, but if we run out of time, at least we want to get through this. And if we have time, then we'll go through an example to illustrate the techniques that I propose. So this is a more detailed slide to elaborate on the 3 components. First of all, the function F. We need to specify function F, the functional form of the dose toxicity curve, and basically this function is used to model the probability of toxicity at dose X. So dose is X is dose here, and beta is the model parameter. And in the SRM, we use a 1-parameter model, so beta is scalar. And then, so in a Bayesian context, again, we need to put a prior on beta. So let's use G to denote the prior distribution of beta. And one important point about the use of the CRM is that the doses we use, the Ds, we select in the CRM are not the actual doses we use, but rather these are dose labels obtained by an backward substitution process. So this is how we do it. So we first need to ask clinicians, or we need to come up with a set of initial guess of DLT rate for each dose. So if there are k doses, we need to come up with k numbers, kp I0. And then we do backward substitution, and then we calculate di by plugging in the prime in the beta, so we set the whole thing equal to our initial guesses of DLT rate. So this is how we get the dose label. And once we identify the dose label, we are going to use the dose label throughout the whole trial. So we don't change that. So, yeah.
So go back to your non-consistent example. If the model is this simple, and if you have a huge number of sample size, and you are saying that under that model is still inconsistent. Is it because of the F is misspecified? Because from just the estimation point of view,
right.
If the model itself is in the range of the two setup you are considering, then you should be consistent, right?
Right. That's a good question. So under the consistent condition, if F is the correct specification for pi, serum is consistent. There's a theorem out there, and the nice thing about it is that for serum to be consistent, F doesn't need to be the right F, so it doesn't need to be the right model. So that's the key point. And but there are various ways that a wrong model can hurt us. So, and as you see, there are 3 components. And so this is the way that I'll get you in next slide. I think. So basically, it's just a way to break down an entire serum model. Again, F, the dose toxic model. This is the most commonly used model functional form. So x raised to power beta. So, and then G is again, this is one of the first prior distribution used. And then the complicated part is the K numbers, the initial guesses of DLT rates. And for some reason, this K number has been called a skeleton. I don't know since when it happened and who called it. Peter thought. So let's just say Peter thought. Skeleton. So from now on, we need to have F, G, and skeleton. Okay, so these
transformation here and take log of AF capital, and then it will be beta times log of AX, and log of AX, it will be new variable U, so the model is K times U.
Right.
Linear model with no intercept.
Right, that's
Just binary.
yeah. So that's actually interesting. The tricky part is how we get the dose label, the skeleton, because by backward substitution, there's some equivalence between there's an equivalent class that define different dose toxic function F could belong to the same equivalent class, which I'm not going to talk about here, because that's actually something we can discuss after that.
But mathematically the same. Yeah?
Well, they're the same actually. They could be the same. That's why they're in the same equivalence class. But actually, this is a good topic that I'm going to pass on this talk. But
so two things.
Okay.
One, you don't observe F, right? You observe 1 or 0. So
right. F is a function that we pre-specify, and this is one particular form of F.
and then there's actually subtle difference.
Sorry, who's chairing this? We're finding it very difficult to follow the speaker's argument because of this material backing and measure. I mean, some discussion is good.
Okay, that was your
I
last
like
question.
the notion that I'm getting too much.
No problem.
See
Yeah.
how
Okay.
I feel, if that's all right.
Okay. Please proceed.
Okay.
Thank you.
Okay.
good.
Thanks. And so just to sort of recap. So again, this is the 3 components, and so I'm going to represent the serum model in these 3 components, F, G, and the skeleton. And so this is sort of the most important slides in the sense that these are the take-home messages. So if you don't know what I'm going to talk about in the next few slides, remember this, and then you'll get what you need. So basically, in literature, there are 3 components. So the natural way to choose, so they are all, choosing all of them simultaneously could be a daunting task. So what has been attempted in the literature is that we fix any 2 components and then calibrate the 3rd one. So in 1993, Sylvie Scheffrey, in the paper in Statistical Medicine, fixed a prior distribution on beta using exponential prior, the standard exponential prior, and a given set of skeleton. And then she basically tried to use simulation to compare different functional F. And then what her conclusion based on the simulation is that I use a logistic function with a fixed intercept, with fixed intercept 3. So this is her conclusion. So this is way back in the 90s. And more recently, my colleague and I tried the other two possible approach. The first approach is to fix the functional form f. We could use the logistic, or we could use some other function, and we fix the prior distribution. And our conclusion is that for any given f and g, we can choose the skeleton to match the operating characteristics. So this is the one of the message. So in this sense, actually, you can choose whatever f you want to use. We still get comparable results. And then, of course, the third natural way to do it is to fix the functional form f, fix the skeleton, and then calibrate the prior. And turns out that there's a sort of somewhat novel concept called least informative prior that we developed, and this generally is adequate. So this will be a take-home message. So again, the game plan is I'll go through these two bullet points in detail. If we can get both, at least we'll get the first one. So choice of the skeletons. Well, again, what is the skeleton? So the skeleton is k numbers. Each number represents an initial guess of DLT rate for each dose. So the most natural way to get this number is from the clinicians who are supposedly who know the drug. So ideally, we should get this number from clinician, and based on the experience. If anyone tried to do that?
Yes,
What happened?
they all died.
The numbers that they give you don't mean anything, just they don't know anything.
Yeah, so basically, yeah, what happened is that what we're talking about, they have all 0. There's no toxicity. So basically what they get is either useless, or the honest one said, we don't know. Well, I mean, and honestly, they can't know. Even after the trial, they can't know for certain. So this is too difficult to do. So the first goal to do the calibration is to reduce the dimensionality of the question, to ask the clinician easier questions, something that's more reasonable that they can answer. So the goal is to reduce these k numbers into 2 numbers.
So
And-
you can count to 5.
And well, but not only 2 numbers, but 2 clinically interpretable parameters. And so these are the 2 numbers. So instead of asking them which number, so k numbers, first ask them out of the k dose level, which dose level you will start the trial. Ask them with the starting dose. And that will serve as the prior MTD, right? So the whole idea of using a SRM is that we treat the next patient at our best guess. So if we start a dose as say a dose nu 0, that will be the assumed prior MTD. So this is the first piece of number that we need to ask from the clinician. The second number we need to ask from clinician is the tolerance for error. So, well, the theta here is actually p. So sorry for the misuse of notation. So it's what happened when you did it in a hurry. So this is p, the target toxicity rate. So this is sort of the trial objective. But we let the clinician know that, well, this is not an ideal world. You don't have infinite amount of information. Give me a margin of error that you will accept. So give me delta. So for example, if you're targeted at a 25% toxicity rate, will it be acceptable if I recommend those that has like 28% toxicity rate? Would that be acceptable? So you basically probe the clinicians to get this delta. So given these 2 numbers and everything else, like the dose toxic function, the number of dose levels, and the prior distribution, we can actually get the skeleton. And instead of telling you the mathematical detail, first I'll tell you how to do it. And this is a very practical talk. And you can get this in our package, the FCRM and the function get prior. All you need to do is to, again, ask the clinician for the margin of error delta. This is, again, the target rate of toxicity that for the trial, the initial, the prior MTD, and the number of dose level. So with these inputs, so this is the trial with a 25% target with a delta of 0.05, it'll give you a skeleton. So there are 5 numbers because we specified a trial with 5 dose levels, And because the fact that we specify dose level 3 as a prime MDD, the third number, so this P03, will have 0.25, which is equal to the target rate. So it's all very consistent with what we do. So basically, this is how we can get from two numbers into the whole skeleton.
I guess this is relevant to the understanding of the procedure. So if I just randomly transform 3 into another scale, would I get a different skeleton?
Yeah, of course, because the
So
key
it's
is that 3 here indicates your prior MTD, and your target is 0.25. You better believe that the dose level 3, the initial guess should be 0.25. Otherwise, you should not be
No,
your
I'm
MTD.
saying I leave other things are unchanged. For example, 0.25 is my target,
Right.
but I can change the unit of my dose level.
Mm-hmm.
So yeah, I can say 3, milliliter per, blah blah, and
Mhm.
I can change the unit arbitrarily, and that becomes 30, for example.
Mm-hmm.
So that's the question I have.
The dose unit or the
It's the same dose, just in different units, but the number will change, right? So that's I'm trying to understand.
You're just meaning the 3 is the index of the dose that is.
no, it's a dose level, not the dose.
It's like 3 pills per day, something like that.
Oh no, 3 is a dose level. It's integer. Yeah, so integer.
It's the third.
Of the-
It's the third.
yes.
It's
Yeah.
it's the index.
It's
Right,
not
right.
the dose.
Not the dose. It's dose level. So it has to be integer. So new 0 has to be from 1 to k. Okay. So yeah, I know I'm skipping the mathematical detail because it's late in the day, but I'll tell you the property of this procedure. I think this is more important for us to understand what it does than how we do it. I think in a certain sense. So the skeleton that the function gets you will have this property. This is what I call an indifference interval. And basically, remember that we asked the clinician to choose delta, so that this will be a range that is acceptable to them. In a certain sense, it's indifferent. It is indifferent to them which dose they choose eventually. So this is the interpretation. So if we choose delta, what happens is that if this is a true dose toxicity curve, which you don't know, but if you draw a window here, which I call the indifference interval, what will happen is that the serum will eventually choose a dose in this range. Okay, so that will be the property of the procedure that I just described. So now you can imagine that if you choose a smaller delta, you're going to have a more precise estimate towards the end, ultimately. So in certain sense, a small delta is good, which makes sense, right? Because you ask the clinician to specify the margin of error, but the smaller the margin of error that you like, you eventually will get a dose that's closest to the true. So basically, this will be the true MTD, but you won't get precisely that, but you get a dose around this, which is good enough, I think.
So is this result independent of how you selected with constants, your skeleton, and shape of function which you select here?
Right,
Theoretical result. I don't.
right.
Just general answer. Does convergence,
Mhm.
what is enter conditions for this convergence? How we selected these 5 doses,
Mhm,
whatever you call it, so skeleton
mhm,
and function,
right,
does it define
right.
convergence? Because I know there are some publications which they say it doesn't converge.
Right. So what happened is, let me think. So let me try to give a short answer to this. So the way I come up with this is to reverse engineer what happened is that in our 2002 paper, we realized that for every single skeleton, we can obtain a delta. So that's the key. So for everything, if we specify a skeleton, we can, for that particular skeleton, we can tell how precise the serum will recommend us to work eventually.
Independently upon true dependence?
Right.
I do not believe in this. If I do
Because the trick is we are controlling on we're controlling on the probability scale. So imagine if you have flatter curve, this region will be wider, right? If you have flatter curve. So what is constant for every single pi is that this window will be a constant, but this region will be wider if you have shallower curve, will be narrow if a steeper curve. Does it make sense to you?
But it doesn't.
It's inter-
If I take very steep
Well,
curve,
Yeah.
and it will be only changes will be within this black interval. So then I'm black hole. That's what I'm trying
Okay.
to understand.
Yeah,
So-
maybe we should have a longer chat after this. But I just hope you would take my word on this, that this is what it does. That if you specify a delta, you'll get a dose eventually around the true MTD. Now, so I thought I made the problem easier by reducing the number from k to 2, and I thought that nu 0, the prime MTD, is relatively easy to get. But delta, you thought it is easy, but it's not that easy. So some clinicians would not even bother to give you the number. So so you probably should ask them. But in case the clinician refuses to give you what the delta is, the next resort is to calibrate it. Thanks. And so again, as I mentioned, asymptotically, a small delta is good, because asymptotically, if a small delta, it means that the dark region will be much narrower. But remember that when we're doing space-on trial, we're talking about sample size from 18 to 30. So what will happen in general is that if you choose a small delta, asymptotically you're smaller bias, but with the final sample size, the MTD selection tend to be more varied. So this is sort of the bias variance trade-off in this form. So the next step of the task is to use simulation to calibrate the prior. So I'm going to do this in 3 steps. So step 1, first we need to specify everything about the model. First we need to choose a function. So let's focus on the logistic function f with intercept 3, and let's fix on this prior and then fix everything else. And so for a target rate of 0.25, because of the way of the acceptable range, delta can be any number that's less than 0.25, right? So what we will do is to iterate delta from a very small value up to a value that's really close to 0.25. So the first step is to iterate delta, and then for each delta, we run the CRM under a set of scenarios, which I call the calibration set. And so basically there are 5 scenarios for 5 doses. So for each scenario, it corresponds to each dose should be the MTD. So the first scenario indicates under the first scenario, the first dose is the MTD, and the second scenario, the second dose is the MTD, and so on and so forth. So we have 5 scenarios. So for each scenario, we run MTD, we run the CRM, and then we get the probability of correct selection under that particular scenario. So basically for each delta, we'll get 5 PCS, 1 under each of the 5 scenarios. And then step 3 is to average the PCS. And then do something simple-minded, which is to take the delta with the highest average PCS. So that's the algorithm. Iterate delta, for each delta run simulation, run 5 scenarios, and then take the average of the PCS and pick the delta with the highest PCS. So this is the PCS for each scenario, but let's look at the average here. So the horizontal axis here is the different delta. In this case, it ranges from 0.01 to 0.24. This line indicates sample size. If you run CRM with sample size 20, this line indicates is a average PCS of CRM with sample size 30, and this is sample size 40. So one thing you realize is that the accuracy increases as sample size increases, so it's going at the right direction. That's good. And the black dot on each curve indicate the position of the delta that maximizes the average PCS. And now what you realize is that when you increase the sample size, the optimal delta shifts slightly towards the smaller end, the smaller number, which makes sense, right? Because delta is an asymptotic property. The smaller the delta, the better. So when your sample size is small, maybe you don't want to choose delta that's too small. But as you increase the sample size, the asymptotic component begins to kick in, and then you want to choose a smaller delta so that the asymptotic bias is getting smaller. So this is actually one way to do it. So this is how I would choose a skeleton. And so for the typical sample size of Bayesian trial with a sample size 20 to 40, basically this is a range of delta that we should use for various target probability rate. And if you want to see a table, there's a reasonably priced book that you can buy and then get the table. And so what will happen is that if you want to run a Salem trial, go to the table, pick and delta, and that's the trial. So how much time do I have?
5 minutes.
Okay, I'll try to go through the second part quickly, which is the choose. So previously we fixed F, we fixed G, we calibrate the skeleton. In this part, we fix the skeleton, we fix F, we want to choose a prior, G. And but G itself is very complicated, is in certain sense very high dimensional. So I will further reduce the problem by make it down to one single parameter. So in this case, again, let's consider a logistic model F with fixed intercept, and let's consider only normal prior. And suppose we have a fixed skeleton. So with this particular prior, the only thing that we need to calibrate is sigma. So you may wonder why I set beta, the prior mean to be 0. There's some equivalent invariance theories that says that the psi mean is invariant to the prior mean. So that part I'm going to skip, but that's good so that I can reduce the number of parameters from 2 to 1. So basically, in this problem, I reduce the problem of calibration to just the calibration of the prior standard deviation. So what's the big deal? I mean, now you reduce it to one tuning parameter. What you can do is to repeat the same procedure. So iterate sigma, run simulation, take average, and compare. So in principle, that's sort of easy, but I actually find quite a few problems. So this is what I did. So basically, I iterate a range of sigma, and then take the average PCS over like 5 scenarios, and this line indicates the average PCS. So you see that for sigma, after this point, the average PCS is pretty close. It's from like 0.49 to 0.51. So it's sort of hard to, well, you could say you choose this point, but they're really close. I mean, it's not very informative or discriminatory in terms of choosing the right sigma, just based on the average PCS. So this is the first problem that I have. So yeah, this is exactly what I just said. The average PCS is quite flat. One sigma is large enough. So what I'm getting at is that maybe we should not use the PCS average as a criterion for choosing a good design. So instead of using the average PCS, remember that we have 5 PCS, one under each scenario, right? So what we could do is to take the standard deviation. And we realize that the difference in the standard deviation is much more like magnified over the range of sigma. And so this is a plot when you plot the standard deviation of PCS against the average PCS, and you realize that actually for sigma with standard deviation smaller, it tends to do better in terms of average PCS. And the reason is that, do I have that in next graph? The reason is that, remember we have like 5 different scenarios. So when your sigma is very small, you see that the variance is big, and so big that under some scenario the SAM does very well, under some scenario it does poorly. So on average, it's pull down the average. So, but as you increase sigma, like around this value, the PZ under the 5 scenarios are very close to each other. So this is where the standard deviation of PZ is minimized, and you actually don't see any particularly poor PZ performance in the particular scenario. But if you keep increasing sigma, you see that again, under some scenario, the salary with big sigma does better, some does poorly. So this is why that there's a negative correlation between standard deviation average of the PCS. So basically, the first problem is to identify a criteria to choose the good design, and the second criteria. So I'm going to skip this one. And so that's another concept that I probably want to talk about because I've negative 1 minute, so I need to wrap it up like in 2 slides. So give me 2 slides. And so this is a concept about, like in traditional Bayesian analysis, you think that if you put a prior with a large standard deviation, that's what we call vague prior. In the context of those findings, that's not necessarily the case, because what we are really interested in is really on the dose scale. So like in this case, if we put a sigma to be 0.2, it is considered an informative prior. You see that under this prior standard deviation, we tend to believe that dose level 3 is the MTD. So in this sense, it's informative. But as we increase the sigma to a big number, 1.16, this is actually more, you would think that it's vague, but it turns out to be even more informative than sigma equal to 0.2. Because if you use sigma to 1.16, it means that you believe that MTD is either 1 or dose level 5. So this is really informative. So what should be non-informative or least informative prior is that we should choose a sigma so that the prior probability of MTD is roughly uniform distributed. So this is what I call the a uniform is the least informative prior, and I'm not going to define it, but what I'm going to show you as a result is that so this is the graph that I've shown you before. That is the average PCS against a different choice of sigma. You would think that this black dot is the dot that maximizes the PCS, the average PCS. It is, but this is not why I put it here. It's the point that achieves the least information in the prior. So it's kind of cool that actually you use the least informative prior, and then you actually identify the right number. So I think this is so cool. And I'm going to show you quickly the simulation results that I used to design trials. So this is the actual study. Under the 5 different scenarios, this is a simulation number that I got from designing the study. So to do this, it took me 2 weeks of simulations, just by try and error. So this is I take the first approach, fix everything else, and then find the optimal delta, and I get this. And then this is the scenario that I fix everything else, use the least informative prior, I got this. You see that they're all comparable. And then you may say, so what's the point? I mean, you could do better by doing like a lot of simulation. But well, the point is, I'm in an environment that a nice investigator will come to me, say,